Good day, and welcome to today's Electronic Design and Microwaves and RF webcast. Our topic today, choosing the right FPGA for your applications, sponsored by Mercury. I'm Bill Wong, Senior Content Director with Endeavor's Design and Engineering Group. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, simply type your issue into the Ask a Question box and a member of our team will assist you. You can also click on the question mark help button in the upper right corner of the screen. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the Ask a Question box and click on the Send button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design and Microwaves and RF websites within the next week. You'll be notified by email when the archive is available. Now let's meet today's speaker. Robert Sangdura serves as Senior Principal Product Marketing Manager at Mercury. He is responsible for product definition, direction, and training for the DSP, data acquisition, data receiver, and software products. Previously, he spent 7 years in the medical electronics industry, where he designed and managed projects for ultrasound imaging. Robert joined Pentec, now part of Mercury, in 1994, working as an application engineer and system integrator, where he concentrated his efforts on solving customers' real-time technical requirements. In 1997, he took on the responsibility of product manager. Now let me turn things over to our presenter. Bob, the floor is yours.
Okay, thanks, Bill. I'd like to start off this presentation with something that I think everybody knows, which is Moore's Law. In 1965, Gordon Moore, who at the time worked for Fairchild Semiconductor and then later went on to co-found Intel, made the observation in an article in Electronics magazine that the number of components in integrated circuits was doubling in about every 2 years. And this often gets quoted as every 18 months, but in an interview in 2005, Moore said he just said every couple of years. But in any case, at the time, Moore had only 5 data points, and with that limited historical knowledge, Moore predicted in the article that this would be an ongoing trend moving into the future. If you take his prediction and expand it out to 2020 and overlay all of the microprocessors produced starting with the first Intel 4004 CPU in 1971, amazingly, his prediction turned out to be very accurate, and along with Dennard scaling, has been used to set the expectation for processor performance, size, power, and cost moving forward. In 1974, Robert Dennard wrote a paper detailing the benefits of processor node shrinks as the transistors themselves continued to get physically smaller with each generation. As a result of the shrinks, capacitance in the node was reduced due to the smaller area of the transistor, voltage was likewise reduced, and transition time was reduced, allowing the transistors to operate at higher frequencies. At the same time, power consumption per transistor was reduced, so as you double the number of transistors in a given physical area, the power requirement stayed roughly the same to operate twice as many transistors in that same physical space. Cost per transistor was also reduced with each node shrink. This chart shows the shrinking geometries of transistors over time, starting in 1968 with 20,000 nanometer nodes all the way down to 5 nanometer nodes in 2018 and 2019, and the promise of 3 nanometer nodes in 2022. And with Dennard scaling, it looks pretty good. But unfortunately, Moore's Law and specifically Dennard scaling have to eventually deal with the laws of physics. As the nodes get smaller and approach the theoretical limit of 1 nanometer, a few things tend to happen. Transistors become more leaky, meaning that even in their off state, some current gets through, and that leakage current goes up as we get closer to the 1 nanometer, losing some of the power advantages we saw at the beginning of the curve. Also, with the extreme miniaturization, the resistance through the node increases. Coupled with the inherent capacitance of the node, switching speeds tend to slow down. In 2015, Gordon Moore did another interview where he said he was surprised that Moore's Law has continued to be a guide for innovation for as long as it has, and he identified a number of the above reasons, as well as the growing cost to produce each process shrink as obstacles to Moore's Law moving forward. A number of strategies have been used to continue to increase performance, including multi-core designs, but even this has limitations because of overall power consumption of the multiple cores and the fact that not all tasks can benefit from parallel processing in a traditional CPU architecture. This chart from a book by Hennessy and Patterson shows the flattening of processor performance over a 40-year period compared to a VAX 11740, which in 1977 was a benchmark, and it includes the performance of CISC processing, then RISC processing, then the diminishing benefits of Dennard scaling on Moore's law, and Amdahl's law, which describes the advantages and limitations of parallel processing, which basically prompts the question, what's next? Another approach is to use specialized processor architectures to match the requirements of specific algorithms and applications. In addition to scalar processing architectures like CPUs, more specialized architectures like vector processing elements, including DSPs and GPUs, and programmable logic found in FPGAs can be applied to specific processing tasks. We find IC manufacturers like Intel and Xilinx, now AMD, integrating different processor types into a single system on chip, or SoC, allowing a kind of best of all worlds type approach to high performance processing. If we look at AMD's latest Versal family of FPGA-based processors, we see a variety of different processors with different features. AMD calls this new family of heterogeneous type processors Adaptive Compute Acceleration Platform, or ACAP for short. And while all have SoC architectures and many common resources, different members of the Versal family have different features that can address different types of processing better than its siblings. So the next question is, which processor type is the best match for different types of processing tasks and development and deployment requirements? Let's break this down into three types of computing elements: scalar processing engines, programmable logic, and vector processing engines. And under vector processing, I divided that further into DSP and GPU. For processing types, CPUs are mainly serial. Scalar processors in the strictest definition of scalar are single instruction, single data, but architectures like ARM support single instruction, multiple data, SIMD, so they're not exclusively scalar, but their execution is still mainly serial. FPGAs, DSPs, and GPUs are all highly parallel. And here when I'm saying DSPs, I'm referring to the DSPs found in FPGAs. CPUs can be used to perform most applications, so I've listed this as general. FPGAs, DSPs, GPUs are all best suited for different tasks, so they're all specialized. ARM processors, x86 processors, are limited to 10 to 20 cores and don't scale well beyond that. FPGAs, DSPs, and GPUs have smaller, simpler processing elements, so they tend to allow greater scaling by adding many hundreds or even thousands of elements. For example, currently available FPGAs are available with 400 DSP elements all the way up to over 14,000 DSP elements. Now, these DSPs are not one-to-one processing equivalents to an x86 core, but the point is a wide range of components are available, allowing you to scale performance to the processing requirements to lower cost and power. CPUs are the easiest to program with a wide range of tools and languages available. DSPs and GPUs are moderate with the tools and languages specialized for the architecture, and FPGAs are typically considered the most difficult. With FPGAs, you're designing the logic that will be instantiated in the fabric, so it's really a very hardware-centric task. But both Intel and AMD have made some major strides in abstracting hardware details through the design tools to allow users to work at a much higher level, not requiring them to be FPGA experts, but in general it's still not as straightforward as development on CPUs. Development time tracks with ease of programming, and again here, long is a relative measurement, right? If you have experience and can, say, leverage FPGA libraries, then you can shorten development time. Typically, code written for CPUs like x86 and ARM is very portable across different processors and even different processor vendors. DSP and GPU code can be more specific to the target hardware, requiring some work to move the code. FPGA designs are usually processor specific. So if you're moving from one processor to another in the same FPGA family, retargeting for the new processor is fairly straightforward. If you're moving across FPGA families from the same vendor, the task is more of a migration task with some code rewriting. And even though AXI4 has become a common interface across IP from different vendors and different sources, moving FPGA design from one vendor's FPGA to another vendor's FPGA will require moving from one architecture to another with different tool chains and different underlying libraries, so that is the most difficult. In general, CPUs are moderately power efficient along with DSP engines. GPUs are typically the least power efficient, making GPU deployment in really large systems like data centers a deployment challenge to meet power and cooling requirements, and FPGAs have the best power to processing ratio. The last parameter I listed is latency, and I call this one out because many military applications are latency sensitive. I have CPUs, DSPs, and GPUs listed as moderate, And here it really depends on the type of processing and data, and if the data is staying on chip or moving off to external memory. But in general, FPGAs are the lowest latency. The logic and by extension the data processing done on the FPGA is tailored specifically to the requirements, so data paths and processing chains are very efficient, keeping latency low. So if I add an additional column for heterogeneous processing like that found in the ACAP, where it might contain CPUs, FPGA fabric, DSPs, and even GPU-like processors, I can compare how it performs. Because all three types of processors are used, you're processing data in both serial and parallel paths. Both general and specialized processing is supported, and scalability of FPGAs, DSPs, and GPUs can be leveraged here. For ease and time of development, I carried the attributes of the FPGA. But again, the FPGA manufacturers are producing comprehensive tool sets to allow access to the programming interfaces at very low levels for FPGA experts who want to operate at that level, but also entry points and the development tools at very high levels to enable scientists and developers who are not programming experts. As I mentioned earlier, you can move an application across from one vendor to another, but it does require a fair amount of work. For latency and power, they both benefit from the FPGA components of the architecture. So here I'd like to use AMD's naming convention so we can see how these processing engines map into the ACAP architecture. AMD calls these scalar engines, adaptable engines, and intelligent engines. This is AMD's diagram of the Versal, and with callouts to the scalar engines, which on Versal are ARM cores, the adaptable engines, which is the FPGA fabric, and the intelligent engines, which are the DSPs and the AI engines. All of the ACAPs in the AI group of processors contain some type of AI engines. So let's take a look at some of these resources, starting with the AI engines. The AI engines are a 2D array of AI engine tiles. They deliver up to 8 times better silicon area compute density when compared with traditional programmable logic DSPs for machine learning implementations, reducing power consumption by a nominal 40%. There are 2 different types of AI engines, which I'll describe in a minute, but the AI engines for machine learning, or the AIE-ML, deliver 4 times AI performance per watt versus a traditional GPU. Deterministic execution is enabled with dedicated instruction and data memories, and dedicated connectivity paired with DMA engines for scheduled data movements using connectivity between AI engine tiles. This provides deterministic execution critical for real-time systems in autonomous vehicles and aerospace and defense applications like electronic countermeasures and a range of other applications. AI engines are C-language programmable, and developers can use library-based design for ML frameworks. There are 2 types of AI engines, the general AI engine tile and the AI engine ML tile. The AI engine tile offers more balanced performance between ML inference processing and advanced signal processing. Some targeted applications include advanced digital signal processing for communications, beamforming, radar, FFTs and filters, and video and imaging processing. The AI engines support a range of real, complex, and floating point data types, with dedicated hardware for FFTs and FIRs. The AI engine ML tile is optimized for machine learning with an enhanced compute core and memory architecture. It's targeted for applications including image and speech recognition, medical diagnosis, statistical arbitrage, and predictive analytics. It has extended native support for ML data types, and its compute core and memory architecture provides a 2 times performance improvement over the general AI engines. Another interesting technology used in system-on-chip is high bandwidth memory. The Versal HBM ACAP features this memory. One way to appreciate HBM is to look at how DDR DRAM matches current technologies. Here I'm plotting the data bandwidths of popular technologies over the past 12 years. Starting with Ethernet, 12 years ago we were at 10 gigabits per second. Then we saw a move to 40 gig. Today we're at 100 gig, and we're quickly moving to 400 gig. 12 years ago, we were watching high-def video at 1K. Then we moved to 2K, and today we're at 4K, with practical 8K capture and playback systems starting to hit the market. DSP processors. Back in 2010, we were happy with 2,000 DSP slices in a Vertex 6. Now we've moved to 12,000 slices, and today we have FPGAs with over 14,000 DSP slices. Data converters are another technology that has moved ahead rapidly. In 2010, we were seeing 12 and 14-bit ADDs at 1 gigasample per second. Then we saw a jump to 6.4 and 10. And now we're seeing converters at 20 gigasamples per second. And recently, we're seeing RF converters at 64 gigasamples per second, allowing us to sample wider and wider bandwidth of the spectrum. What these technologies all have in common is a need for memory, for buffering, and as a processing resource. If we chart the bandwidth of DDR DRAM memory over the past 12 years, we went from DDR3 to DDR4 and now DDR5. But what we see is a much more conservative increase in bandwidth capability compared to the technologies that need it. We see traditional interface DDR memory is just not keeping up with the bandwidth requirements of many of these popular technologies. One solution is high bandwidth memory, or HBM. HBM puts the FPGA and the DRAM in the same package, and this removes the PCB material, the routing complexity, and the speed bottlenecks of external memory. The data transfer bandwidths of up to 820 gigabytes per second are achievable, and that represents about an 8 times increase in bandwidth compared to traditional DDR5 DRAM. External memory interfaces are eliminated, replaced with on-chip traces, realizing a power savings of 63% lower power. Discrete DRAM footprints are removed from the board, enabling more compact circuit designs and reducing board layers needed to connect memory to FPGAs, and that can lower the cost of the PCBs. And HBM-enabled processors are physically larger than non-HBM equivalents, but the increase is much smaller than the space needed to hang, let's say, 8 or 10 discrete memory chips, memory chips off of the FPGA. HBM provides unique data throughput while addressing swap requirements. Another technology that is starting to enable higher system performance in a wide range of different applications is having the RF data converters on chip with the processors. AMD's version of this is a direct RF block of their Versal architecture. Unfortunately, this is the last member of the Versal family to be released, but I think this technology is so important that I want to look back at the previous generation of RF SoC parts in AMD's Zinc UltraScale Plus family. In a typical data acquisition board, it helps to look at how the data converters, the A to Ds and the D to As, are interfaced to the FPGA. 3 options are parallel LVDS interfaces, serial JESD204 interfaces, and on-chip interfaces of the RF SoC. In a typical parallel interface data converter, there are differential pairs for each data bit and usually an additional pair for clock. In a serial interface converter using JESD204 protocol, there are typically less pairs of wires, but these are running at much higher data rates and carry the serialized data over less pairs. In the case of RF SoC, the data converters are on chip with their data moving over parallel interfaces right on the FPGA fabric. So how do each of these compare in PCB design requirements, data path latency, size, power, and cost? To connect to the converter shown in green, each bit gets a wire pair that needs to be length matched, so the data of all the bits arrives at the FPGA at the same instant, and this complicates PCB design. These interfaces are usually limited by the speed of the FPGA interfaces and top out at around 1 GHz. For JESD, or JESD204, less signal pairs need to run on the PCB with less concern for length matching because the JESD protocol aligns the data and these interfaces are running at higher speed to handle the data bandwidth. In the case of RF SoC, the interface signals are all on-chip, eliminating PCB routing completely. I mentioned that the LVDS interfaces are speed limited. So if you want to run at a higher data converter sample rate, you can't move the data faster over the LVDS lines, so you have to multiplex the data and run it over multiple LVDS interfaces. This again complicates the PCB design and adds PCB costs because of more routing layers. We see the solution also tops out at around 6.4 gigasamples per second with converters currently on the market. Another parameter is latency, which here I'm defining as the amount of time needed for the signal to enter the A to D and propagate through the circuitry to a point where the digital representation of the data is needed. So if I compare the 3 interface types, parallel interfaces introduce the least latency at about 50 to 90 clock cycles. Close to parallel is RF SoC with 86 to about 166 clock cycles, and serial interfaces like JESD have much longer latencies in the range of 1600 clock cycles or more, making those converters a mismatch for low latency applications. So what are low latency applications? Well, first let's take an application that isn't low latency. In a data recording system, the signal is received, it's digitized, and then it's sent to some storage device. In this case, you might not look at that data for a second or a day or a year. So as long as you don't drop any data, the latency is not a problem so that any of these solutions could work. Electronic countermeasures, on the other hand, is very latency sensitive. A signal like a radar pulse is received, then it must be processed to create a return signal that represents a target that is different than the actual one, and the signal must be retransmitted to the radar receiver. All of this must happen in a very low and deterministic latency, so parallel LVDS or RF SoC would be a good match. For a size comparison, I took the gate density of the RF SoC and found another FPGA with the same density and drew it to scale. The RF SoC has 8 A to Ds at 5 gigasamples per second, So I found a discrete serial A to D in about the same sample range and drew them to scale. Same thing with the parallel A to Ds. I did the same with the D to As. One problem you run into, though, with high sample rate parallel converters is the amount of signals you need between the converters and the FPGA. With 112 signals needed for each converter and a total of only 600 signals available on that FPGA, you can only connect 2 A to Ds and 2 D to As, halving the number of supported channels. I did the same with the ARM processor, finding processor chips that were about the same size as the ARM core that's in the RFSoC. What you end up with is the RFSoC solution is 1600 millimeters squared, the JESD solution is 2860 millimeters squared, and the parallel solution is 3210 millimeters squared. And considering many of these systems get deployed in UAVs and other SWaP-constrained environments, the RFSoC comes out ahead. Comparing power needed for these solutions, RFSoC again comes out ahead. And in cost, the RFSoC is the lowest, with the JESD solution costing about 1.6 times more than the RFSoC, and the LVDS solution costing about 1.9 times more than the RFSoC. So again, even though the Versal AI RF isn't available yet, it will produce advantages similar to the current RFSoC, but with higher performance. One last piece of the puzzle is the network on chip. One of the biggest obstacles of domain-specific processing in heterogeneous systems is moving the data between the different processing resources. If the board or the chip interfaces become bottlenecks, you can quickly lose that processing advantage of using specialized hardware. The programmable network on chip addresses this. It enables high bandwidth interconnects between resources, and it's a flexible crosspoint supporting multiple simultaneous data paths. It supports an aggregate data bandwidth of over 1 terabit per second. It frees logic resources from being used for these interconnects. It shares device access to DRAM and DDR memory. It supports programmable logic to programmable logic connections. It provides memory access to the AI engine array. It supports connections between the processing system and the programmable logic. And it supports connections between PS and DDR memory. Throughout these slides, I've been using this block diagram, and this is like the super Versal. It shows all the possible resources of the Versal on one block diagram. But each member of the family trades off some resources for others, so understanding what resources are available in each part is important. You can see these differences in all the different block diagrams of each part, but they're kind of hard to actually appreciate, so I'd rather do this with a table. So we can compare the AI Edge, the AI Core, the AI RF, the Prime, the Premium, and the HBM. All of the chips have a network on chip connection. They all have scalar engines, the ARM Cortex processors. They all have FPGA fabric. They all have intelligent engines, the DSPs, intelligent engines. And for the intelligent engines, the AI type, the Edge and the Core have that. I have a question mark on the AI RF because while we know they have AI engines, we don't know what kind will be in there. Prime does not have AI engines, and neither does HBM. But interestingly, I have a question mark on Premium because if you remember from before, the Premium was not part of the AI family. But Xilinx announced earlier this year that they're going to start shipping Premium with AI engines. It's not clear yet which ones, but they will have actually a very high count of AI engines in that Premium part. The intelligent engines, the AI ML engines, are in the AI Edge and the Core. Again, we don't know what's going to be in AI RF. They're not in Prime, they're not in HBM, but they could potentially be in the Premium once they start shipping that. The high bandwidth memory is only available on the HBM part. The direct RF will only be available on the AI RF part. Some of the chips have video decoder engines, both the Edge and the Core do. I don't know if AI RF will, and I know that Prime, Premium, and HBM don't. As far as the PCIe interfaces, basically all of them support Gen 4. Edge and Core have discrete, and so do Prime and Premium have discrete Gen 4 engines in them. The HBM actually has only a Gen 5, but it can always drop back to Gen 4. And the only one that doesn't have a Gen 5 is the Edge. So if you're looking to run PCIe Gen 5, don't use the Edge part. As far as the multi-rate Ethernet Max, they basically all will support 40 gigs. I have dashes there again because they're not discrete 40 gigs, but they're multi-rate, and the faster 100 gigs can support the lower rates. So the Edge doesn't go up to 100. Everybody else does, and then the 600 gig is only supported on the Premium and the HBM. So again, looking at the requirements for your application, looking at what is available on each one of these Versal parts can help you decide, which is the correct which is the correct FPGA for your application. So I hope this presentation helped you with that decision. And I think that was my last slide. So if we have any questions.
You mentioned quantum computing. Is there another option?
Yeah, quantum computing will be an option, but I think right now it's a little early. Companies like IBM and Google, and there's a third, D-Wave, are producing prototypes, but they're still very expensive and they have some really demanding cooling and maintenance requirements. So I think users today can access them via the cloud, but it's pretty limited. I think the current estimates are that we'll see quantum computing become more practical and readily available in like mid 2030s. But interestingly, Mercury has two customers, Duke University and the University of Maryland, that are actually using our RF SoC boards from the previous generation of FPGAs in their quantum computing labs. So it's an interesting tie-in.
Okay, next question is, how does the analog performance of the RF SoC data converters compare to dedicated and discrete A to Ds and D to As?
The data converters on the RF SoC look very good. And I'm talking about, again, one generation back. We're not at Versal AI RF yet, but we will be. But on that previous generation, and in general, a concern might be that having the A to Ds on the same substrate as the digital components would be a problem. But spurious free dynamic range on the A to Ds is better than 70 dBFS. Channel to channel isolation is better than 70 dB. So they look as good as dedicated, off-chip converters would look.
Okay, so when will the Versal RF series be available?
AMD hasn't announced a Versal AI RF release date yet. It's definitely on their roadmap. They have it on their website. I'm guessing we'll see something probably next year. But if you do have a requirement that that requires, or you think it requires AI RF, I would just reach out to your local AMD FAE, and he could probably share more info with you than I can.
Okay, so what's the best way to get started with Versal?
So I guess it depends on what you mean by getting started. Right now, AMD has a lot of information on their website about Versal. There are white papers, tutorials. I think the data sheets are all up there, except for maybe the HBM. That's a newer one, but that might have been released now too. And of course, AIRF isn't there yet because it hasn't been announced. So for general information, the AMD site is a really good place to start. If you want to start working with actual Versal hardware and get hands-on experience, you have a few different options. Mercury has a COTS 6U VPX Open VPX board called the Skiffy 6931, and that's SCFE 6931. The board's available today and has two Versal AI core parts. It also has 8 by 4 lanes of optical, so you can actually run 800 gig interfaces in and out, which is you need that kind of data throughput for the kind of processing you might want to do. We also have announced a 3U SOSA aligned Versal HBM board that's called the Model 5560, which will be available in the first half of 2023. And this board has a mezzanine site for hosting high-speed data converters, so which makes sense because, again, those data converters will need the kind of bandwidth you can get on the memory with HBM. So if you're looking to do just Versal for IP and software development, you don't necessarily need to deploy it. AMD has eval boards for all the released Versal parts, and you can find those eval boards on the AMD site. Or again, if you're looking for information on the boards I mentioned from Mercury, you can find them on the Mercury site.
Well, I'm afraid we've run out of time. For those questions we didn't have time to answer, we'll be getting back to you via email. This concludes today's presentation. On behalf of Electronic Design and Microwaves and RF, I'd like to thank Mercury for sponsoring today's event, and of course to all of you for joining us. Have a great rest of the day.